These will be your notes for Unit 4, Day 3 of Pre-Calculus. If you would like to see the warm-up, the review question, or any of the homework questions that we covered in class today, just look at the finished notes. So today we're going to move on from polynomial functions and we're going to talk about rational functions. So remember, the word rational has the word ratio in it, which is a comparison of two numbers or a fraction. So these are going to be like polynomial fractions. So rational functions are like polynomial fractions. So you have a polynomial in the numerator and a polynomial in the denominator. We're going to talk about their different characteristics, their domain, intercepts. They have things called holes, which means you're traveling on their graph. And then all of a sudden you have a point that doesn't exist on the graph, and then it just keeps going in the same direction that it was traveling in before. That's called a hole. You have asymptotes. They have both vertical and horizontal asymptotes. Those are dotted lines that are like boundary lines on the graph, which your graph won't cross. And then we're going to be able to graph our rational functions. So rational functions and their domain. So rational functions, again, are your polynomial fractions. So we could have the most basic one, which would be your parent function. And maybe you guys remember how to graph this parent function, which we're going to review in a second. But it has a vertical asymptote and a horizontal asymptote on the axes, and then the function itself hugs those curves. So that's the parent function for the rational function. So what's the domain? Remember, domain are your x values, and in a fraction, the denominator can't equal 0. So whatever makes the denominator 0 is a domain restriction. So for this one, x can't be 0. So the domain is every real number except for x is equal to 0, or if you're going to put that in interval notation, it can go from negative infinity to 0, and then it can go from 0 to infinity, but it cannot include 0. A more complicated one could be like x plus 2 over x squared minus 9. So again, for the domain of any rational function, the denominator can't equal 0. So x squared minus 9 can't be 0. And then you can factor and solve this. So this is a difference of two squares. So x plus 3, x minus 3 can't equal 0. So your domain is x can't be negative 3 and x can't be positive 3. So you can list it like that, and that's fine. Or if in interval notation, it can go from negative infinity to negative 3. It can go from negative 3 to positive 3. And then it can go from 3 to infinity. So it's showing that it can be every number but negative 3 and positive 3. All right, let's say we have h of x equals x squared plus 4 over x squared minus x minus 12. So again, for the domain, the denominator can't be 0. So for in this case, x squared minus x minus 12 can't be 0. So again, we're going to try and factor and solve it. This would factor into x minus 4, x plus 3. So those can't be 0. So x can't be 4 and x can't be negative 3 for the domain. So finding domain of rational functions, you just, whatever the denominator is, say that it can't be equal to 0, solve it, and those are your domain restrictions. So again, we can call these domain restrictions. So graphing rational functions, the parent function. So there's two different types of rational functions. You have the basic one, so 1 over x. So remember, to graph, we can just start plugging in x values. If I plug in 0, I get an undefined. If I plug in 1, I get 1. If I plug in 2, I get 1/2. If I plug in 1/2, I get 2. If I plug in negative 1, I get negative 1. If I plug in negative 2, I get negative 1/2. If I plug in negative 1/2, I get negative 2. So 0, it doesn't equal. It's undefined. 1, 1, 2, 1/2. If I did 3, it'd be 1/3, 4 would be 1/4, 5 would be 1/5, so it's getting closer and closer to 0. And then if I plug in 1/2, I get 2. If I plug in 1/3, I get 3. 1/4, I get 4. So on this side, it's this picture. So it's getting closer and closer to 0 as the x values are getting big. And then as it's getting closer and closer to the x value of 0, the y values are shooting up. And then on the other side, I have negative 1, negative 1, negative 2, 1/2, negative 3, 1/3, negative 4, 1/4, negative 5, 1/5, and then negative 1/2, negative 2, negative 1/3, negative 3, and so on and so forth. So this side would look like that. So it's never going to cross the x-axis or the y-axis. So there's the parent function of just 1 over x. 1 over x squared I call the volcano function. Let's figure out why. So if I plug in 0, I get undefined. If I plug in 1, I get 1. If I plug in 2, I get 1/4. If I plug in 3, I get 1/9. If I plug in -1, I get -1. If I plug in -2, I get 1/4. If I plug in -3, I get 1/9. If I plug in 1/2, I would get 4. If I plug in 1/3, I get 9. And then same thing for the negative of those. So 1, 1, 2, 1/4, 3, 1/9. And then if I plug in 1/2, I get 4. If I plug in 1/3, I get 9. So on that side, it's looking like this. And then notice, since it's 1 over x squared on the other side, oops, not -1, that's +1, I get -1, +1, -2, 1/4, -3, 1/9, -1/2, 4, -1/3, 9. So it mirrors itself on the other side. So I call that the volcano function because it's erupting at the x-axis. So that's what the parent function of 1 over x squared looks like. And then just like with any other function, you can use the parent function to graph using transformations. So for this one, the parent function moved up 2, and then it was reflected up down, or it was reflected over the x-axis. So we're going to take our parent function, which looks like this, and we're going to move it up 2. So now it's up to here. And then the piece that was up is going to go down, and the piece that was down is going to go up. So this guy's going to look like this and like this. And you can check on Desmos to make sure that that looks like a good sketch. On the next one, this function moved down 2. It moved right 1. And those were the two transformations that happened. And so it's 1 over x squared. So the parent function is the volcano. So I'm going to move this down 2 and right 1. So that's going to move those lines, which are called asymptotes. So down 2, right 1, and then it's going to still shoot up like a volcano, but it's just down 2 and to the right 1. So you can graph rational functions using transformations. Well, what if it's not easy to see the transformations? Well, then you need to know what all of the different pieces are when we graph them. So two of the things that we can talk about are vertical asymptotes. So those are the dotted vertical lines that the graph doesn't cross. So our graph doesn't cross a vertical asymptote. So a graph doesn't cross the vertical asymptotes. And I'm going to abbreviate vertical asymptotes VA because it's a long word to write. So I'm going to, whenever you see VA, I'm talking about vertical asymptote. And then the holes, remember we talked about briefly, it's a break in the graph. So the graph was going, and then all of a sudden it doesn't exist at a point, but then it keeps going like it did. So to find vertical asymptotes and holes, your first step is you are going to factor the numerator and denominator. So to find vertical asymptotes and holes, you're going to factor the numerator and denominator of your rational expression. And then step 2 is you can cancel. And then step 3 is you're going to set the denominator equal to 0. And whatever's left, those are going to be vertical asymptotes. So whatever makes the denominator equal to 0 after you factor and cancel is going to make vertical asymptotes. Whatever cancels makes the holes. So what do I mean by that? Well, let's look at our first example. So if I take A, first step would be to factor the numerator and the denominator. It's already factored, so I don't need to do anything. Nothing cancels, so there's going to be no holes. And then you would take what's left in the denominator, set it equal to 0, and solve. So x equals 1. That means that I have a vertical asymptote at x is equal to 1. So on my graph, he would have a vertical asymptote where x is equal to 1. Let's look at our next one. X over x squared minus 4. So the numerator doesn't factor, but the denominator factors into x plus 2x minus 2. Nothing cancels, so there's no holes. And then you set the denominator's pieces equal to 0. So x plus 2 equals 0, x minus 2 equals 0. So either x is negative 2 or x is positive 2. So this means that this graph has two vertical asymptotes, one where x is equal to 2 and one where x is equal to negative 2. Let's look at another one. So let's look at H. So we have x squared over x squared plus 1. Nothing cancels. The numerator is a monomial and the denominator is a binomial. Monomials and binomials cannot cancel with each other. So binomials cancel with other exactly the same binomials. And since the top is not a binomial, nothing will cancel. So there's no holes. And then I would take the denominator, set it to equal, and solve. So x squared equals -1. That's going to have no real solution. So there's also no vertical asymptotes. So that graph is going to have no holes and no vertical asymptotes. And let's look at our last one, D. So factor the numerator, x plus 3 over x minus 3. Factor the denominator, x plus 7 over x minus 3. Notice the x minus 3's cancel. So if something cancels, you take whatever cancels, set it equal to 0, and solve. And that's going to be a hole. So there's a hole when x is equal to 3. So there's going to be a break in the graph right there with a hole in the middle of it. Then you take what's left in the denominator, the x plus 7, set it equal to 0, and solve. And so that means that this graph is going to have a vertical asymptote at -7. And then at x is equal to 3, I don't know where it's going to be on the graph, but there's going to be a hole there. That's just a sketch. That's probably not what the real graph looks like. So those are vertical asymptotes and holes. So again, to find vertical asymptotes and holes, you factor the numerator and the denominator. Whatever cancels after you factor, that creates a hole. Whatever's left in the denominator, set it equal to 0, and those make vertical asymptotes. Horizontal asymptotes. So horizontal asymptotes are the asymptotes that go left and right, and they tell you about the end behavior of the graph. So what are the tails of the graph doing? So there's 3 different rules for horizontal asymptotes. So to find horizontal asymptotes, you play the degree war game. And the degree war is you have to find the highest exponent. So whatever term has the highest exponent wins. And there's 3 options. Option 1, what happens if the denominator wins the degree war? So for example, if we had f of x equals x over x squared plus 1. Notice the denominator has the highest degree of x squared. So when the denominator wins, you automatically have a horizontal asymptote, and I'm going to abbreviate those HA. You have a horizontal asymptote at y equals 0. So on the graph, your horizontal asymptote would be when y is equal to 0, or the x-axis. So if the denominator wins, it has the biggest degree, you have a horizontal asymptote at y equals 0. Option 2, what if it's a tie? So the numerator and the denominator have the same degree. So we have g of x equals 2x squared minus 4 over 3 plus 5x squared. So again, the numerator has a degree of 2 and the denominator has a degree of 2, so it's a tie. So when it's a tie, you look at the ratio or the fraction of the leading coefficients. So the leading coefficient of the numerator was 2. The leading coefficient of the denominator was 5, because you had 2x squared over 5x squared. So the horizontal asymptote would be at the fraction of those numbers, so 2/5. So this graph would have a horizontal asymptote at 2/5. Option 3 is what if the numerator wins? Well, if the numerator wins, we have h of x equals x squared plus 2 over x minus 1. If the numerator wins, then there's no horizontal asymptotes. Instead, you have something called a slant asymptote. And we'll talk about those in a second. So let's look at the examples. So who wins in that first one? Well, we have a 2x squared over a 1x squared, so this is a tie. When it's a tie, the horizontal asymptote is going to be at the ratio of their leading coefficients, so it's going to be at 2 over 1. In the next one, we have 2x over negative 3x. Again, it's a tie, so the horizontal asymptote will be at the fraction of their leading coefficients, so negative 2/3. On the next one, we have an x cubed in the top and then an x squared in the bottom, so the numerator wins. So there are no horizontal asymptotes when the numerator wins. On the next one, we have x over x cubed. The denominator wins. When the denominator wins, the horizontal asymptote is at 0. And on the next one, we have 2x squared over 8x, so the numerator wins again. When the numerator wins, there are no horizontal asymptotes. There would be none. So we've talked about vertical asymptotes, holes, and horizontal asymptotes. Oblique asymptotes, which your book calls, they're also called slant asymptotes. So if you want to find oblique asymptotes, they're when the numerator wins. Unfortunately, in order to figure out what they are, you have to do long division. So let's review how to do long division. So we're going to take 2x to the 5th. It's missing an x to the 4th term, so I'm going to put 0x to the 4th, then minus x to the 3rd, then plus 0x squared, plus 0x, and then plus 2. I put those in so I don't get confused when I'm dividing. And then it's going to be x cubed minus 0x squared, or plus 0x squared, plus 0x minus 1. And then we have to think x cubed times what would make the 2x to the 5th? Well, that would be 2x squared, and then just like normal division, multiply this out. So it would be 2x to the 5th plus 0x to the 4th plus 0x to the 3rd minus 2x squared. And then in long division, you subtract going down. So we would get 0, 0, and then we would get negative x cubed, and then we get plus 2x squared, and then we would bring down the 0x, and we can bring down the 2 if we want to as well. And then we think x cubed times what is negative x cubed, and that would be negative 1. And then we distribute again, so that would be negative x cubed minus 0x squared minus 0x plus 1. And then subtract going down, and we would get 0, we would get 2x squared, and we would get 3. That is our remainder. We would get 2x squared plus 3, so we put the remainder over what I divided by, so 2x squared over 3 divided by x cubed minus 1. And then that numerator helps us find the oblique asymptote. So when we're trying to find oblique asymptotes, that's what we're going to do. Zeros and intercepts of rational functions. So if we want to find zeros, zeros are just another way of saying the x-intercepts. And then intercepts, in this case we're talking about the y-intercepts. So remember, to find x-intercepts, you let y equal 0. To find y-intercepts, you let x be 0. So to find the y-intercept, so let's find the y-intercept, we're just going to let x be 0. So this would be r at 0 would be 0 minus 1 over 0 squared minus 4, which would be 1/4. So my y-intercept would be at the point 0, 1/4. To find the x-intercepts, again, you're going to let y equal 0. So we would have 0 equals x minus 1 over x squared minus 4. The only way for a fraction to equal 0 is when the numerator equals 0. So the only way to have an x-intercept is when the numerator equals 0, but you need to cancel first. So factor and cancel first. So this would be x minus 1 over x plus 2x minus 2. Nothing cancels, so the only x-intercept would be when the numerator equals 0. So I have an x-intercept at 1, or at the point 1, 0. So again, to find a y-intercept, you let x equal 0. So and then this next one, I would get 0 squared minus 1 over 0, which is undefined, so there are no y-intercepts. To find an x-intercept, factor and cancel, so x plus 1 over x minus 1 over x, nothing cancels. So x-intercepts are when the numerator equals 0. After you factor and cancel, so I have x plus 1 is equal to 0, x minus 1 is equal to 0. So this graph would have x-intercepts at negative 1 and positive 1. So negative 1, 0, and 1, 0. So putting that all together, we can graph rational functions. So notice this is not going to be easy to graph by just using transformations, because we have x squared plus 5x plus 6 over x squared minus 9. So what I recommend doing first is factor. So let's factor the numerator and the denominator. So this would be x plus 3, x plus 2 over x plus 3, x minus 3. So the domain, remember the denominator can't equal 0, so x plus 3 times x minus 3 can't be 0. So x can't be negative 3 and x can't be positive 3. So for the domain, x can't be 3 and x can't be negative 3. For our vertical asymptotes and holes, notice what cancels. The x plus 3 cancels, so I have a hole at what cancels. So I have a hole when x is equal to negative 3. So you take whatever cancels, set it equal to 0 and solve, and that's going to make a hole. You have vertical asymptotes with what's left in the denominator. So what's left in the denominator is x minus 3. So I'm going to have a vertical asymptote at x is equal to positive 3. For horizontal asymptotes, remember you play the degree war game. And who wins? Well, it's x squared over x squared. It's a tie, so it's the ratio of their leading coefficients, which is 1 over 1. So I have a horizontal asymptote at y equals 1. X-intercepts, you let y equal 0, or it's when the numerator equals 0 after you cancel. So what's left in my numerator is x plus 2. So I need x plus 2 to equal 0. So I have an x-intercept at negative 2, 0. To find a y-intercept, you let x equal 0. So if I let x equal 0, I'm going to get y equals 2 over negative 3. So I'm just going to factor or plug it into x plus 2 over x minus 3. If I plug a 0 in for each of those x's, I get negative 2 over 3. So I have an x-intercept at 0 and then negative 2/3. So let's go ahead and graph our asymptotes first. So I have a vertical asymptote at x is equal to 3. So at x equals 3, I'm going to make a vertical asymptote. I have a horizontal asymptote at y equals 1. So at 1, I'm going to make a horizontal asymptote. Now I'm going to do any of my points. Well, I know that I have an x-intercept at negative 2, 0. So I know it's going to cross the x-axis right there. And then I have a y-intercept at negative 2 or 0, negative 2/3. So I know it's going to cross the y-axis right there. Well, it looks like it's going to be following these guys. We can do a couple more points to help us, but it looks like this one, this piece is following this. And then I'm guessing that the other piece would be reflected up here doing the same thing. But to test it, let's just test what happens if I plug in one of these points. So that's 1, 2, 3, 4. So let's test what happens if x is equal to 4. So in my reduced form, I would have y equals x plus 2 over x minus 3. If I plug in 4, I get 4 plus 2 over 4 minus 3, which is 6 over 1, so 6. So at 4, I should be at a height of 6. So this guy should be a little bit higher than what I drew it. So 1, 2, 3, 4, 5, 6. So this guy should look like that. So what's the only thing that I haven't graphed yet is the hole. I have a hole at x is equal to negative 3. So that's 1, 2, 3. So right here at x equals negative 3, I need to make a hole on that graph. So you're just going to make an open circle on the graph right there at x is equal to negative 3. And we can check our guy on Desmos. So let's see how close we were. So we had, it's a rational, so let's put our numerator in parentheses. X squared plus 5x plus 6, and then divided by x squared minus 9. And that looks pretty good. So notice it had, our intercepts look good. It looks like it has a vertical asymptote at x is equal to 3. And then if I follow this along until I hit x equals negative 3, notice it's undefined there. There's a hole there. So we look like we did a good job. All right, let's try another one. So again, the first step is to factor the numerator and denominator. So we have x plus 2, x minus 2 over. I'm going to pull a 3 out of those. So 3x squared minus 5x plus 6. So this is going to be 3 times x minus 2, x minus 3. So the domain, the denominator can't equal 0. So x can't be 2 and x can't be 3. So for our domain, x can't be 2 and x can't be 3 because that's what makes the denominator equal to 0. The x minus 2's cancel. So we have a hole when x minus 2 equals 0. So we have a hole at x is equal to 2. What didn't cancel makes the vertical asymptote. So what's left in the denominator is x minus 3. So when x minus 3 equals 0, we have a vertical asymptote. So we have a vertical asymptote at x is equal to 3. The horizontal asymptote is the degree war. So who wins? Well, it's a tie again. So I have a horizontal asymptote at 1x squared over 3x squared, or 1/3. So I have a horizontal asymptote at y equals 1/3. And then your x-intercepts, remember, are after you factor in cancel, it's what makes the numerator equal to 0. So what's left in the numerator is x plus 2, and x plus 2 equals 0 when x is equal to negative 2. So I have an x-intercept at negative 2, 0. To find your y-intercept, you let x equal 0. So if I plug 0 in for x, I have x plus 2 over x minus 3 times 3. After I plug in the 0, I get 2 over negative 9. So I get a y-intercept at 0 and negative 2 ninths. All right, so let's go ahead and graph these one at a time. Let's start with our asymptotes. So I have a vertical asymptote at 3 again. And then I have a horizontal asymptote at 1/3. And then we'll plot our points. So I have an x-intercept at negative 2, and I have a y-intercept at negative 2 ninths. So again, this one looks like very similar to the last one we drew. So it looks like it's going to do that. And then I'm going to guess this one mirrors it, but we can test a point. So this is 1, 2, 3, 4. So we can test what happens if x is equal to 4. So if I plugged in 4, I would get 4 squared minus 4. Well, let's plug it into the reduced version, actually. The reduced version is x plus 2 over 3 times x minus 3. If I plug in 4, I get 6 over 3, which is 2. So that should be 2 high. So 1, 2. So it should actually be there. So let's make this guy look a little bit more accurate. And so that would be the second piece of our graph. And the only thing that's missing is I should have a hole at 2. So at 2, I'm going to make a hole right there. So there's my hole at x is equal to 2. All right, so this one's a little bit different because the numerator wins. So this one is going to be an oblique rational function. So let's go ahead and go through the same process. So factor the numerator and denominator. So this would be x times x plus 2 over negative 4 times x minus 2. So nothing cancels. So there's no holes. The domain is x can't be 2. The vertical asymptote is x is equal to 2 because that's what makes the denominator 0. Your horizontal asymptote, notice the numerator wins, so there's none. So we're going to have to find the slant asymptote, but let's find our intercepts first. Our x-intercepts are what makes y 0, or it's what the numerator is. So x times x plus 2. So I have an x-intercept at 0 and at negative 2. So at 0 and negative 2, I have x-intercepts. Y-intercepts, we're going to plug in 0 for x, and I get 0 over 8, which is 0. So I have a y-intercept at 0, which is that same point. So we're good. So now I have to make the slant asymptotes. So to find a slant asymptote, we're going to have to do some long division. So we're going to take x squared plus 2x plus 0, and we're going to divide that by negative 4x plus 8. So negative 4x times what is x squared? That would be negative 1/4 x. And so if I multiplied that out, I would get x squared, and then negative 1/4 x times 8 would be negative 2x. And if I divide that out, I get 0. So it goes in cleanly. So that means that negative 1/4 x is going to be my slant asymptote. I think that I said the wrong part up above when I was talking about the slant asymptote. I'm going to go back up and change that in a second. So y equals negative 1/4 x plus 0 is going to make a slant asymptote. So if I were to graph that, we would start at 0, then go 1 down, 4 over, and then since it's an asymptote, we're going to make a dotted line. And then we had a vertical asymptote at 2. So those pieces are going to divide this graph. So let's go ahead and see what our graph looks like on Desmos. I feel like something went silly somewhere. So we are going to do x squared plus 2x and then divided by negative 4x plus 8. And then we have, nope, my slant asymptote's wrong. And then our vertical asymptote's right. And then those guys look to be okay. Well, he just needs to be a little bit more exact, I guess. So he looks like this. And then he shoots up, and then he looks like this, and he shoots down. And so we just need him to be a little bit better. So we need to look at that horizontal asymptote again. or the slant asymptote. All right, so what if we want to write an equation for a rational function? So let's start with the vertical asymptotes. So my vertical asymptotes on this graph are x equals -5 and x equals 2. That means if I put them back in the parentheses, I'd get x plus 5 and x minus 2. And remember, vertical asymptotes occur in the denominator. So I have x plus 5 and x minus 2 have to be in the denominator for those to be vertical asymptotes. My horizontal asymptote is y is equal to 2. So for that to happen, that means that the numerator and the denominator need to have the same degree. Well, the degree of the denominator, when I multiply that out, would be x squared. And so the numerator also needs an x squared, and it needs to have a 2x squared for this to work. And then we are going to look at the zeros. Well, I know that I have a 0 at x equals 5, and I have a 0 at, it looks like, x equals 2. So that means that I need an x, minus 5 and an x plus 2. So we have x-intercepts at x equals 5 and x equals 2. So we would need, -2. So that means if I put them back in the parentheses, I would need an x minus 5 and an x plus 2. And remember, x-intercepts happen in the numerator. So we have an x minus 5 and an x plus 2 in the numerator. And then I need a 2 out in front for that horizontal asymptote. And since we found our zeros, we found our asymptotes, that graph should match, so this equation should match that graph pretty well. Let's go back up to where I talked about slant asymptotes, oblique asymptotes before. Nope, that's 2x squared as well. We're going to have to review oblique asymptotes again during the live lesson.